Okay, so this would be a reasonable reaction for us to have happen here. So we said that if a Grignard has a choice, it would rather act like a base and not a nucleophile. If a Grignard has a choice, it would rather act like a base and not a nucleophile. But this Grignard has no choice. There are no good hydrogens for it to steal. There are no good hydrogens for this Grignard to steal. The only good hydrogens to steal are hydrogens on electronegative atoms, especially oxygens. And all the hydrogens here are on carbons. So Grignards don't steal hydrogens from carbons. That's an important point. Why doesn't the Grignard steal the hydrogen from the hydronium?
Because
Why does it attack the carbonyl and not attack the hydronium?
there's another positive charge on the oxygen.
Sorry. So yeah, let's go through that. Now actually, we just did an example where the Grignard did attack a hydronium, right? If you just go back in your notes, the very last example we had was where the Grignard did attack the hydronium. The reason is the hydronium hasn't been added yet.
Oh.
Right? Remember, that's what these numbers mean over here. Maybe that was a mean trick question, but that's something that's important to understand for the test. These numbers mean that these are being added as two separate steps. So what we're doing is we're taking our beaker or our flask, and what are the two things that we're putting in the beaker? Well, I guess we're starting with the Grignard. We start with the Grignard, and then we add this aldehyde. And then we wait before we add the hydronium. This number 2 here means that we're waiting. We don't immediately add the hydronium. We wait for the first reaction to finish. We wait for the first reaction to finish, and then we add the second step, the hydronium. Well, that allows the Grignard to attack the aldehyde here, because there's nothing else in the flask or the beaker for it to attack. Make sense? Okay. Okay. So this explains why we have to add this hydronium only after we've done the main reaction with the Grignard. We were already talking about this. Remember we said you have to keep Grignards away from protic solvents. And even more, you have to keep them away from acids. Protic solvents and acids wanted to protonate Grignards. You have to keep them away until the Grignard's done the reaction that you want it to do. All right. All right, so now we can draw the product from here. Now, one technique that I don't think either of you used here was numbering. I really encourage you to get in the habit of always numbering whenever the product is at all in doubt. Remember, these are not IUPAC numbers. Go ahead and use the same numbers I'm putting on the board, just so that we're all doing the same thing. So I'll call these carbons 1, 2, and 3. Now, should I call this carbon 1? Well, no, I should call these carbons 4, 5, and 6. Because these are not the same carbons here. You don't want to give the same number to two carbons unless they're the same thing. So I'm going to give different numbers to these because they are different atoms. And now I'm going to go through step by step here, drawing the product. So first of all, I'll start with the number 1 carbon. Who's the number 1 carbon attached to? 2. Who's the number 2 attached to? 3. Who's the number 3 attached to? 4. Who's the number 4 attached to? 5. Now let's stop for a second. Is there anybody else the number 4 is attached to? Oxygen. Now it's single bonded to an oxygen, because we broke this double bond over here. And we know that the oxygen now has this pair. I'll go ahead and put the electrons in. Here's the pair of electrons that the Grignard donated, and here's the new lone pair that this oxygen has. We're keeping track of those pairs, even though you technically don't have to do that. Is there anyone else that the number 4 is bonded to? Yeah, that's kind of a matter of taste, whether you draw that hydrogen. Remember, we usually draw aldehyde hydrogens, but we usually don't draw hydrogens over here. Maybe I'm going to draw that just because it was kind of around in the reaction. But you could draw this or not, whatever you like. That doesn't matter very much. Okay, so far so good? All right, only once we're done with what number 4 is attached to, now I'm going to go on to the number 5. What's the number 5 attached to? 6. And the number 6 is not attached to anybody. And now, very important, every time we do a step, I have to change 2 charges. So I go to the initial tail. This started negative and it's losing electrons, so it ended up neutral. So that's good. And who's at the final head? This oxygen. Well, this oxygen started neutral and it's gaining electrons, so it ends up negative. By the way, remember that the formal charge has nothing to do with these partial charges. When we're doing formal charges, it has nothing to do with the fact that it started with a delta negative. Okay. All right, and now we're in pretty good shape here. We've changed all the covalent bonds. How about the ionic bonds? Well, this lost a charge, so it's losing its ionic bond to the magnesium bromide, and the oxygen gained a charge. So we can draw in a new ionic bond to the magnesium bromide over there. All right, so this would be a good product. All right, so I think that you almost had this right, except I think that you lost a carbon. I think if you look at your picture, you lost the carbon, and that's going to lose you a lot of credit on that problem. It's a very common mistake to accidentally add a carbon or drop a carbon. So how do you prevent making that mistake? By numbering all the carbons. If you number all the carbons, it makes it very much harder to lose a carbon. So this is a really important technique that we should try to use on any predictive products problem. From now on, that's not totally obvious to us. This should be the default. The only time you shouldn't number is when the problem is boringly easy. But if it's not boringly easy, let's put the numbers in. Notice how the numbering works. We gave different numbers to these carbons because they're different from each other, but we gave the same numbers to these carbons because they're the same. And we give the same numbers to these carbons because they're the same. So don't just number the starting materials, number the products as well. Now the other technique that I used is, notice I did not try to draw this in one fell swoop. The one fell swoop technique does not work. I drew this one atom at a time. Think back to all the little questions I asked you. Those are the questions you have to ask yourself to get the right product. I started with the number 1 and I asked, who's the one attached to? Number 2. Who's number 2 attached to? Number 3. And I only drew in each part when I specifically thought about it. So I didn't accidentally choose anything was wrong. Who's the number 3 attached to? Number 4. Who's the number 4 attached to? Number 5. And then I asked myself, is the number 4 attached to anybody else? You have to go back and make sure that you put in all the attachments that everyone has. So you have to get in the habit of asking yourself those questions yourself. Notice it took me a long time to draw this. There is no fast way to do this, except once you've done 100 of these, you can kind of do them quickly. But the first few times, you've got to do it very step by step. So this is a good technique for drawing the products. It's the take your time technique, basically. Okay, so that gives us this. All right, because losing a carbon is not a small deal. That's very important here. Okay, so that gives us what we have over here. And now I guess we're ready for the next step. So now let's add the hydronium. So let's try drawing the mechanism for what's going to happen there. See what you got so far. Oh, you're just getting started? Okay. Well, let's go through this together. Who is the most reactive atom here?
The oxygen.
The oxygen, because it has a charge. Should it be at the head or a tail? Tail. So I'm going to start by putting the oxygen at a tail. This is a useful technique. Remember that you saw in the second language book, every arrow has 2 parts, a head or a tail. A lot of students don't like to draw an arrow until they know both parts. But you should draw the arrow as soon as you know one of the parts, and then you can put in the other part. All right, now who would be a good atom to put at the head here? The hydrogen. What's the oxygen acting as now, a nucleophile or a base?
Base.
It's acting like a base. Is an oxygen with a negative charge a good base? Yeah, you know from your SN2 handout, an oxygen with a negative charge is a good base. And it doesn't really even have to be a good base because this is very acidic because it has a positive charge. So this should definitely protonate. All right, again, it might be tempting to have the oxygen attack this oxygen over here. But again, then this oxygen would be acting like an electrophile. And so far we've only seen carbon electrophiles. And also, remember this positive charge is really spread over the whole molecule. So really, since the hydrogen started with more positive charge than the oxygen, maybe it still has more positive charge, is one way to think about it. All right, and then we have to break this bond over here. All right, so this is our standard deprotonation reaction over here. Eventually, you should just have to memorize that this step is deprotonation, so you don't have to think it through so much. All right, so the oxygen has formed a bond to the hydrogen. The oxygen started negative and it's at the initial tail, so it ends up neutral. This oxygen started positive and it's at the final head, so it ends up neutral. The initial net charge was 0, and now the final net charge is, oh, am I getting confused? Actually, the initial net chart, so let's finish up here. One point is I'm not going to bother drawing this old aldehyde hydrogen anymore. That's not really interesting. Now, we're going to have to break this ionic bond. Since the oxygen lost its negative charge, we're going to break that ionic bond. So the magnesium is not bonded to it anymore. And actually, at this point, no one ever pays attention to the magnesium anymore. So I guess maybe the magnesium is going floating off somewhere. I guess you might say the magnesium is over here, but no one ever does that. Once we go on to the second step here, no one ever pays any more attention to that spectator ion, that magnesium bromide. So I'm not even going to bother writing it here. So you might want to have that in your notes. When you add the protonation step for a Grignard, you can just ignore the counter ion from that point on, because there's nothing for it to counter anymore. There's no charge for it to balance. Okay, so that would give us this product over here. Okay, this is a really crucial reaction, so it's very important to have this memorized. This will be important on the test, but also you're going to use this for the whole rest of the course, this semester and next semester.